And so like this. This is a discussion of relativistic quantum theory. And one particle states. So we will define a certain type of quantum states which correspond to single particles. These are these one particle states, and they have then certain Lorentz properties. So the first thing that we need to say in a relativistic quantum theory is a quantum theory is based on a Hilbert space of physical states. And if we want to have Poincare invariance, we first must define what it means to say we have a Lorentz transformation. So that in particular means for every quantum state in our theory, we must be able to say what is its Lorentz transformed version. We must define something how to transform quantum states between reference frames. And that means we need a representation of our Poincare transformations. Representation U of lambda comma a representation of Poincare transformation on our Hilbert space of states. Okay. So that means we must be able to define for any state I, we must define a new state I prime, which is obtained by performing a Poincare transformation with lambda a, and this is defined by this representation lambda of a acting on I. So this means first of all that our Poincare transformations are linear, so they are represented by linear operators. That means if you have a linear combination of states, the Lorentz transformed version is again the linear combination of the transformed states, because we have here a linear operator acting on our Hilbert space of states. So the, let's say, linear combination property of quantum mechanics is preserved under Poincare transformations because we represent it by a linear operator. And then of course the group property of two different Poincare transformations back to back are preserved because of the representation property of this U of lambda a. So now we know how each quantum state transforms, and we can obtain transformed states. But that is not yet invariance of under Poincare. Now we need to say what does it mean that the theory is invariant. And in particular, the physics predictions of the quantum theory should be invariant under such Poincare transformations. And the very, very most basic predictions of any quantum theory are always scalar products, which are probability amplitude whose square gives you probability. So the most basic objects in a quantum theory are scalar products. And so when we say we need invariance of all predictions, then the most fundamental invariance would be the one of any scalar product between two states f and I. So this scalar product under lambda a should on the one hand go to f prime I prime, but it should be the same as the original scalar product. If this property holds for all states in the theory, then for sure the physics predictions are Poincare invariant. Now, this relationship implies something about our representation U of lambda a. Namely, what does it imply? If we have here the transformed states, we can plug in the definition. So I prime is U acting on I. F prime is also U acting on F. So if we plug it here, we have to dagger it. So here we get F and I, and in between we have U dagger times U, the product of the two operators U dagger and U. So if this should be the same as the original scalar product, it means that the combination U dagger U must be the identity operator. That is our condition. So this means U dagger of lambda A times U of lambda A must be the identity operator. And this relationship means that the operator U is unitary. So in other words, we have a unitary representation. And I think then this is a good point to stop. In one word, a relativistic or Poincaré invariant quantum theory is a quantum theory on which we have defined a unitary representation of the Poincaré group. As simple as that. That is the condition for any relativistic quantum theory, unitary representation of the Poincaré group. And then we can go to representation theory, generators, P mu, J mu, and derive consequences, and we will do that tomorrow, and then we can answer the question that I posed on one-particle states as well. Okay, so see you tomorrow. With our lecture from yesterday, we are in the middle of a certain topic, namely we are defining relativistic quantum theories in full generality. Every relativistic quantum theory must have a definition of some operator, U of lambda and A. What is the meaning of this operator? It implements Poincaré transformations on the space of our quantum states. It's a linear operator, and it's a representation of the Poincaré group. So for every Lorentz transformation and every translation, there is a certain operator U of lambda and A. It has the representation property, so group multiplication laws are reproduced on the level of this operator. It's a linear operator, so it acts on quantum states in the appropriate way such that linear combinations are preserved. And it is unitary, which means that scalar products or probability amplitudes are also preserved under Poincaré transformations, and that means the physics of the quantum theory is invariant under these Poincaré transformations. So this operator defines a relativistic Poincaré invariant quantum theory. And now we can go to the infinitesimal level. Laws are reproduced on the level of this operator. It's a linear operator, so it acts on quantum states in the appropriate way such that linear combinations are preserved. And it is unitary, which means that scalar products or probability amplitudes are also preserved under Poincaré transformations, and that means the physics of the quantum theory is invariant under these Poincaré transformations. So this operator defines a relativistic Poincaré invariant quantum theory. And now we can go to the infinitesimal level. And as always, we write infinitesimal Poincaré transformations with a Lorentz transformation which deviates a little bit from the unit matrix and a small translation. And for any representation, we have defined the Taylor coefficients of these small transformations, and we can also do it here, therefore, and write U of delta plus omega comma epsilon. So this is this infinitesimal Lorentz and translation, and again it's given by the unit operator plus I times epsilon mu times p mu minus I over 2 omega rho sigma times j rho sigma. This is the completely general decomposition, and by definition this quantity here p mu is the Taylor coefficient of that in front of epsilon. That is the Taylor coefficient in front of omega rho sigma. And in this way, from our representation, which is unitary, we define here certain quantities p and j, and they are of course also operators which act on the space of quantum states, because U of lambda A acts on the space of quantum states. So those are also operators on our Hilbert space in the quantum theory. And because of the I here, and because that is unitary, it automatically implies that these are Hermitian operators. So our representation defines Hermitian operators P, mu, and J, rho, sigma on our quantum theory. And so let's write that down. They are Hermitian because that is unitary, and by definition they now have a certain meaning, namely this is of course by definition our four-momentum operator of our quantum theory, and this contains the operator for angular momenta, namely J12 is equal to J in Z direction and so on, but it also contains boost operators. So automatically every Poincare invariant quantum theory contains a definition of Hermitian momentum operators and angular momentum and boost operators, which also act on the space of quantum states. So that is our
طبعا هذه الطريقة بعدين سنحسب بها تيار نيثر وسيمتري عن طريق تيار نيثر وما إلى ذلك. لهذا الأمر هذه الجزئية مهمة جدا، اللي هو البي والجي مهمة جدا، لأنه سنطبق عليها معادلات طويلة عريضة وسنخرج منها بسيمتريس حسب نظرية نيثر.
was set up for a relativistic quantum theory, and on such theories we can now define a notion of what we call one-particle states, or a definition of particles. So we can now come up with the most general definition of what we mean by a particle and write that down. So you can think a little bit in physics terms. What could be properties of actual single particles in contrast to states which are composed of several particles or some other states which have not a characteristic of a particle. So what defines a particle for you in physics? And one simple definition of a particle is something that has the property, if you fix its location or its momentum, then its state is essentially fixed. Something like that would be a particle. Whereas any other state, like two particle states, is fixed not by specifying one position, but you need to specify something in addition, the relative position between the different particles or relative velocities and so on. But for a single particle, the simple definition is that its state is defined once you specify where the particle is. And there are just some exceptions, namely particles might have something like a spin, an internal degree of freedom, which is a discrete additional quantum number. So up to the beyond the position, the only thing that might be different for particle states might be a discrete choice of the spin that you can assign. So that is our definition of single particles, namely objects whose states are completely defined by just specifying the location and possibly a discrete choice of the spin. Location in that sense is equivalent to specifying the momentum. So equivalently you might say, once you specify the momentum and the spin of a particle, its state is fixed. And any object which has this property will now be called a particle. And so for us, particles are not only elementary particles, but also there are composite objects which classify as single particles. And for example, an example is the hydrogen atom. The hydrogen atom in its ground state behaves exactly in that way, because the hydrogen atom in the ground state is completely fixed. Once you specify where the atom is, the state is uniquely defined. There is no other internal degree of freedom. All hydrogen atoms are exactly identical in the ground state, up to maybe they are at different positions or they have different momenta. So a hydrogen atom in the ground state classifies as such a single particle. Even more complicated molecules in a ground state would classify as such single particles in that sense. And of course, that also holds for the proton. The proton state is completely fixed by specifying its momentum and maybe specifying spin up or down in some direction. Yes?
If you have a larger molecule, wouldn't the rotation or spatial alignment also?
Degrees of freedom or different states the molecule can be in, but if the molecule has one unique ground state, then the ground state, for example, would be rotationally invariant, and then the ground state is uniquely specified by the overall momentum of the molecule or the location of the molecule. And then there are no rotations excited, that's why it's in the ground state, and then there are no such internal degrees of freedom. So the subtle additional information is that one needs to say a molecule in the ground state or a hydrogen atom in the ground state. Then this classifies as a single particle in the sense that we are going to define. But a molecule overall, as you say, has of course many internal degrees of freedom, and it can be in many different states beyond the location and beyond the momentum. Right. And for example, for the proton, you might also say, okay, why is the proton state uniquely fixed by its momentum? It is uniquely fixed because even though the proton is like a molecule, the proton has some inner constituents, and these inner constituents, the quarks and gluons, they might also be in some excited states. But if they are in some excited states, we don't call the thing the proton anymore. The proton, by definition, is exactly the ground state of this ensemble of three quarks and some gluons. And the excited states of the same quark content would be called other baryons and not protons anymore. And so from that point of view, a particle is an object whose state is uniquely defined by specifying the momentum or the position and maybe a discrete choice of the spin. So let us write that down. So the state is uniquely characterized by the momentum and the spin, but I write spin in quotation marks because we have not yet completely defined what actually a spin means. And of course one should also specify the particle type. So that in particular means that there is no continuous inner degree of freedom. So a basis of states could then be written as like this. A stands for the particle type, P stands for the momentum eigenvalue, and S would be this discrete spin in quotation marks, which we still have to investigate what it actually means. So then, because that is our definition, it means that all states of a certain particle type can be transformed into each other by a Lorentz transformation or by a translation. So if you translate a hydrogen atom from here to there, then you get a new state, and so on. So all basis states are of, let's say, type A, are connected by Poincaré transformations. So they differ only by their momentum, by their direction, or by their location, by nothing else. That means if you take one state, you can reach any other state of the same particle type by applying some of these u of lambda and a. So any state can be reached from any other one by applying this u of lambda and a. And on the other hand, if you apply any u of lambda and a to a state, you obtain a state of the same particle type. So Poincare transformation does not change the type of the particle. Does not change the type. And these three items here, they mean something mathematical, namely on the space of states of this particle type, we have defined the action of this u of lambda and a. The action of u of lambda and a does not lead out of the space of states because the particle type is not changed. And any state can be reached by the u of lambda. So that means mathematically the u of lambda and a defines or is defined as a representation of the Poincare group on the space of states of this particular particle type, and that representation is irreducible. So it doesn't lead out of the space, and any state can be reached from any other one. There is no invariant subspace. So that means mathematically we have an irreducible representation of the Poincare group. So the space of states of type A forms an irreducible representation u of lambda and a of the Poincare group. And that can also be used as an equivalent, more mathematical definition of a particle type and of one particle states, because this mathematically summarizes all of what we have said before. And so if we have a representation which is irreducible, then we have had these Casimir operators. Let me first write down the Casimir operators. These were p square and w square. P square is the operator for the rest mass square, which is a Lorentz invariant quantity. And w square is this other Casimir operator, which probably means something like spin. This is also Lorentz invariant. So these eigenvalues of those operators are Lorentz invariant. If we have an irreducible representation where every state can be reached from every other one, it means that those eigenvalues must be the same for all those states, because they are Lorentz invariant and any state can be reached. Therefore, these eigenvalues of these two operators are universal. They are specific for every particle type. Every particle type has a certain eigenvalue of p square, which is then the rest mass for that particle type, and a certain eigenvalue of w square, which would be something like the spin of that particle type. So we have fixed eigenvalues of these two operators. So rest mass and spin are fixed for any type of particle. They cannot be changed. Okay, so with this we have defined our one particle states, and then we can come to this final subsection of this chapter here that I announced yesterday, where we want to derive something really deep and interesting about the possible types of particles, which includes also more information on what this spin in quotation marks actually is, depending on some other properties of the particles. So this section is possible one particle, how did I call it, representations. Just check something here. So if we want to write a basis for our one particle states of a certain particle type, let's call it A, then we can think, like in quantum mechanics 1, what is the set of commuting operators, and then we can simultaneously diagonalize certain operators and write down a basis according to those operator eigenvalues. So here our commuting operators are, first of all, p square commutes with everything, w square commutes with everything, and then p mu, all the components commute with each other. So for sure, here we have already 6 operators, all of which commute with each other. So we can simultaneously diagonalize all those operators. These are not interesting for us now because they have certain fixed values. We don't know which ones, but they are fixed anyway, so we do not use them as labels of our states. But these are, of course, very important labels, which are the momentum eigenvalues. So for sure, we'll use them in our basis. But then there are other operators as well, which might commute with all of them, but we are not yet determining which other operators there are, because it will depend on some other details, which operators we should choose here. Therefore, our states will, for particle type A, let us label them in a simplified way, simply like this, P, S. So to be compact, let us not write always the label A, because anyway in this section we are only dealing with one particle type A, and so we label it only with the eigenvalues of the P mu operator. And then there might be some other label, let's call it S, like spin, but we have to determine what that other label actually means. And that is what we are going to figure out. So we know, as we said before, that this U of lambda in A defines an irreducible representation of on these states here. So all states are obtained from any other state by acting with U of lambda and A. So the translations are uninteresting. Translations are obtained by exponentiating the momentum operator as usually, and we already know the behavior of the momentum operator. Therefore, we also know the behavior of translation, so we do not have to take into account translations. Therefore, that is not interesting to discuss. And so what is interesting to discuss is the effect of Lorentz transformations lambda. For Lorentz transformations U of lambda, there are two interesting cases to consider. What are those two interesting cases? If you imagine you act with U of lambda on exactly such a state with some given P and some given S, then two things can happen. Case A, which is the normal case, this U of lambda changes the momentum of your state from P to lambda times P. You do a boost or some rotation of your momentum. So that is the, let's say, normal case. Lambda changes P to lambda times P, which is different from the original P itself. So you do some Lorentz transformations which does something non-trivial to your momentum, and then you can assume that the other label, however, is left intact. Okay. Second case is the opposite. Namely, there are certain Lorentz transformations which do not change the momentum P. So P is going always to lambda P, but it can happen that lambda P is actually the same as the original P. So a certain Lorentz transformation which doesn't change the momentum. This can happen. And if that happens, then the only thing that Lorentz transformation can do is it must do something non-trivial with this other label, whatever it means. But this Lorentz transformation can do all sorts of things, all possibilities to this other label. Yes. Okay. And then of course there can be combinations. There can be combinations where you change both, but it's clear that you can at first separate the two cases and study only changes in momentum or changes only in the other label. And afterwards you would combine it. And so in the references that I gave you yesterday, in particular in Weinberg's book, you can find a very long discussion where he goes through all those different steps, but it's quite clear which is the more interesting case for us. The more interesting case is of course the second one, where the momentum is kept intact and we only change something with the other label, because if we investigate that, it gives us the full information on what is this additional degree of freedom of the particle beyond the momentum. That gives us all the information we might need about behavior of the spin, the nature of the spin, possible values of the spin. This is obtained just from that. And once we understand this, we can change the momentum as well, and then we have the full picture. But it's essentially sufficient to study only the second case. Let me write it here, of course, all combinations. And so, in the lecture here, we will focus only on the second case. Focus only on B, because that gives us information on the internal degree of freedom. And therefore on the meaning of spin. And in order to focus on this, it is also not necessary to study any random value of the momentum. It is possible and sufficient to select a very simple certain special momentum and study then all Lorentz transformations which keep that particular special momentum intact, and because we could always transform to any other momentum by this kind of Lorentz transformation. So it's sufficient to consider a certain special momentum value. Once we would have done that, we can obtain the rest and the completely general case from this. And we will not do all of that here, but you can find this in the literature. But we will consider here the essential point, which is the degree of the inner degree of freedom for a special momentum. And so actually let me clean the blackboard immediately so that we have some space to write down some interesting tables. Because I want to do now case distinction. In our case of Poincaré invariant theories, there are two very differently behaving kinds of particles. And this case distinction is not possible in a non-relativistic case, but in a relativistic case we need to distinguish between particles with rest mass 0, which move with the speed of light, and particles with rest mass non-zero, which move with speed less than the speed of light. And the first kind doesn't exist, obviously, in a non-relativistic theory. So these will be our two cases, mass 0 or non-zero mass. So maybe let's order it like this. Here we then might have the conclusion, but here let us write down some table. Here mass square non-zero, and here mass square equal to 0. So it will not be so much, but let's nevertheless order it like this. And of course, the left-hand side is familiar to you from non-relativistic physics, because here we could go to the rest frame of particles, and then the speed might be very slow. So whatever you know from the non-relativistic limit should have some simple kind of generalization here, whereas that is completely different, maybe. So we want to choose now some standard momentum. Let's call it K mu. K mu is a standard momentum, and let's choose some standard momentum for a particle with rest mass non-zero. What could be a good choice for a standard momentum for a particle with rest mass non-zero? That could be the particle at rest. Particle at rest is certainly the simplest possibility. So the momentum for vector is simply this, rest mass and then zero momentum. So that is a good choice, certainly always possible. And then let us investigate these internal degrees of freedom. In other words, all possible Lorentz transformations which do not change this momentum. But first, let's also do the contrast here. What could be a standard momentum for massless particle? K mu. What kind of 4 vector could you choose? Any ideas? So this is not possible. No?
So 0, C, 0, 0? Moving just in the x direction with C?
This is not the velocity but the momentum. So the momentum also has an energy component. So and the energy is not 0 if it has a spatial momentum and some velocity. Its energy cannot be 0. And and the momentum is not the velocity c, but it's some value of momentum. So let's let it move in the z direction. Okay, and the energy, however, cannot be 0, but it must be the same as the spatial momentum, and then the square of this momentum, k square, k mu, is 0 with this assignment. So that would be a possible choice. Okay, so you suggested in x direction, let me suggest in z direction, then my notes are more compatible. But anyway, that is the standard choice. So we choose, of course, one simple direction, and we choose here z direction. The particle moves in z direction, of course, with the speed of light, and that means the spatial momentum has the same value as the energy in natural units. So that is our standard momentum, and you see, obviously, there is no limit in which that reduces to this, so the two cases are really distinct. Now, we need to fulfill what we have planned here, or outlined. We want to focus on particular Lorentz transformations which have the property that they do not change the momentum, because these Lorentz transformations might still do something non-trivial to the particle, but they do not change the momentum, so they must change something else. They can only change the spin. So here, what are the possible Lorentz transformations which do not change this momentum, this 4 momentum? And by the way, the set of all such Lorentz transformations is called the little group. It's called the little group of Lorentz transformations specific to this K mu. It's the group of Lorentz transformations which leaves that invariant. And so you know that Lorentz transformations in principle, you can denote them by rotations and boosts. So there are 3 possible rotations around the 3 axes and 3 possible boosts along the 3 axes, and so you can now ask yourself, which of those leaves that thing here invariant? The rotations, and around any axis, of course, leave this invariant, because the rotations only change the spatial components and they do not change this component at all. So this is invariant under all rotations. Is it also invariant under any boost in any along any axis? All rotations. No, it's not invariant under any boost, because whatever you do, if you go to any moving reference frame, you automatically change here the coefficient. You multiply this with this gamma factor from the boost, and so that component will change, and you also create some non-zero momentum, some really spatial momentum in some direction from your boost. And so it's precisely invariant under all rotations and only under rotations, nothing else. So the little group is exactly the rotation group, lambda mu nu, with the form. So here is just 1, and then we have here some rotations r, which is an element of SO3. Okay. So the little group is simply the ordinary rotation group. What are the group generators? What are the group generators? The group generators of this rotation group are the angular momentum operators. So J, X, Y, and Z, or equivalently J 23, 31, 12. Those J's are the generators of the little group. If we apply them, our momentum doesn't change. If we apply any other generator of Lorentz transformations, but not one of these, then the momentum will change. Okay, so we now know the little group, and we know which kind of Lorentz transformations we may apply in order not to change the momentum, but in order to change the spin index. So it's exactly the rotation group. What about here? Here we will get something different, and so we will learn now something about the possible spins of massless particles. So what is the little group of this momentum? Which Lorentz transformations leave invariant this momentum? It's clearly not all rotations, because in general, if you do a rotation, you change this k here into those components. Therefore, this is not invariant under all rotations. However, it's invariant under some rotations. Yes?
Rotations around the
Right, exactly. So around the z-axis, then only these are interchanged somehow, but they remain 0. So let me write it. Lambda mu nu is equal to Kronecker delta mu nu plus omega mu nu. And so just some formulas. What we need to have is that omega mu nu k nu is equal to 0, where omega mu nu is equal to minus omega nu mu. And what we want to write down is the most general omega mu nu. And actually I choose here to write it in infinitesimal form, because it's much easier to see in infinitesimal form what you can do in order to leave this invariant. And your answer is already a first answer, namely rotation around this axis. How do infinitesimal rotations around the z-axis look like? They just look like this, that you would have here in the middle cosine theta, sine theta, minus sine theta, cosine theta. And infinitesimally, cosine theta is just 0, minus theta, plus theta, and 0. That is the infinitesimal form, just sine and cosine expanded in first order of theta. So, and if you see, if you act with this omega onto k, then you get 0, of course. So that times this gives a 0 for vector. And then clearly you are right, this defines a certain Lorentz transformation which leaves this invariant. But what else can we do? What else can we do? We cannot do a rotation around any other axis. For example, if we do a rotation around the x-axis, then the k and the 0 get somehow exchanged. But we can correct for this by following up the rotation with a certain boost. If we combine such a rotation which generates here something non-zero, then we do a boost afterwards which makes that 0 again. That is possible. And so a certain combination of rotations plus boosts can also leave that invariant. And this is easy to see in infinitesimal form. In infinitesimal form, we simply need here an infinitesimal matrix which maps that to 0. And let me just give you an idea. So if you write here something, what should we write? For example, let's write here B into that column. That B would correspond to some B minus B. That would correspond to a rotation around the x-axis. That corresponds to a rotation around the x-axis. In the same way as this corresponds to a rotation around the z-axis. Okay? That is a rotation around the x-axis. So if we apply this onto that 4 vector, we do not get 0 because that B hits the k over there. And so we do not get 0. However, if we write here minus b and then apply it onto that 4 vector, or plus b in fact, plus b because it's lower index, plus b, if we apply it now to this 4 vector, we get 0. So that b corresponds to a rotation around the x-axis, and that b corresponds to a boost in the y-axis. And so the combination of the two maps that to 0. So if we interpret this as an infinitesimal Lorentz transformation, then it leaves this momentum invariant. And so we can fill up this matrix in a similar way. So if we have here minus a plus a, then this would correspond to a rotation around the y-axis. This corresponds to a rotation around the y-axis. And it doesn't leave it invariant, but if we write also here minus a, then it leaves it invariant. So it would be a rotation around the y-axis followed by a boost in the x direction. Okay, and now we have to fill the entire matrix. The matrix should be antisymmetric, so let's make it antisymmetric. So here we must have 0 in the diagonal. Then we have here minus a plus b minus b, and here we have 0. So this is a matrix with 3 independent parameters, a, b, and theta, and it corresponds to rotation around the z-axis and this certain combinations of the other rotations with certain boosts. And you can check again at home that really this matrix, if you act with it onto that 4 vector, you always get 0 no matter what a, b, and theta are. So that shows you that also here we have a little group of Lorentz transformations which leave this momentum invariant, and the little group has 3 independent parameters. So it's a 3-parameter Lie group. It's a Lie group with 3 different generators. And so what are the group generators analogous to this here in the right case? So in order to figure out what is exactly this combination of the j's which leave it invariant, you can plug in this expression 1/2 omega rho sigma times j rho sigma. This was our term in the expansion of our representation. And if you now plug in this form for the omega matrix, multiply with j rho sigma, then you get certain terms. For example, you get here minus theta, which is the 1,2 component, minus theta times j12. So you get j12 times minus theta and so on. So let me write down minus theta times j12, plus you get a times j13 and here minus A times J0, 1, and so on. So let me write it down, plus A times J3, 1 plus J0, 1 plus B times J2, 3 plus J2, 0. So this is our set of generators, and that means this generator leaves our momentum invariant, that generator leaves our momentum invariant, and this generator leaves our momentum invariant. So we get particular combinations of J components, and let's give them some names. Obviously, I will call that capital A. So this is capital A times this coefficient A, and I call that capital B. It's the coefficient of that B over there. And then we have 3 generators of our little group, but they are not the angular momentum, but they are angular momentum in Z direction, and the 2 combinations A and B, certain combinations of specific rotations and boosts. So you first of all see that the little group which leaves the momentum invariant is different in the case of a massive particle and a massless particle, and the little group corresponds to the internal degree of freedom, in other words to the spin. Therefore the behavior of spin and the nature of spin, the meaning of spin, is different for a massive particle and for a massless particle. This is the first important physics result that we learn here. Actually, I think the statement here fits nicely here. So let me write down a statement which is at the same time an exercise for you.
هنا أنا أريد أن أقول كلاما استقرائيا ربما يكون صحيحا أو خاطئا. انظر إلى المتغيرات الكثيرة في حالة السبين الماسلس اللي هي الماس يساوي 0. هناك متغيرات كثيرة وكل متغير يؤثر في الثاني، وبالتالي حصلنا على معادلات كثيرة من أجل أن نجعل هذا الجسيم invariance في الجراوند ستيت، في حين الجسيم الذي يحتوي على الماس الأمر عنده مختلف. فماذا يعني هذا؟ في نظري أن هذا كلما زاد المتغيرات زاد تأثير الكتلة على الفضاء ثنائي الأبعاد، وبالتالي نحصل على متغيرات كثيرة في حالة زيادة الكتلة وفي حالة تسبب تهديد للفضاء ثنائي الأبعاد. فلعل هنا الماسلس بارتيكلز هو هي بارتيكلز كتلتها تساوي 0 بحسب رؤيتنا نحن، في حسب وضعنا نحن كملاحظين، لكن بحسب وضعها هي ربما كتلتها تكون لا نهائية أو كتلتها تكون كبيرة بحيث أنها تشكل تهديدا للفضاء ثنائي الأبعاد، أو ربما ليست الكتلة وإنما الشحنة مثلا. يعني في الفوتون ربما نقول أنه الشحنة هي التي سببت هذا. لماذا؟ لأن الفوتون يتفاعل من ناحية الشحنة، وأيضا يظهر في الكتلة عند النشاط الإشعاعي. النشاط الإشعاعي يمكن نقول أنه يتفاعل أيضا بكتلته، لكن الأغلب تفاعلات الفوتون هو كهرومغناطيسي، فلهذا يمكن أن نقول أن الشحنة هي سبب ذلك. بالرغم من صغر حجم الفوتون صغير جدا جدا، لكن فضاء، والفضاء طبعا متصل، الفضاء الذي يحيط به هذا الفضاء يراه كبيرا جدا. هذا الفضاء صغير يرى هذه الشحنة كبيرة جدا بحيث أنها تسبب تهديدا له. لهذا نجد أن المتغيرات كثيرة جدا في الماسلس بارتيكل، وبحيث أن نجعل السبين لا متغير أو invariance، فإننا علينا أن نضبط ليس فقط السبين وإنما أيضا البوست اللي هو دوران الفريم اوف ريفرنس. يعني حتى البوست يجب أن يدخل في هذه المعادلة، في حين الماس بارتكلز نجد أننا فقط نجد أن المومنتوم أو الام الكتلة هي أصلا انفاريانس حسب نظريتهم هم، وصحيح في حالة فري بارتكلز، لكن في حالة السبين هو فقط الجي هي أيضا الجي جنريتور تعتبر انفاريانس، لكن يعني الجي الام والجي كل واحدة منفصلة عن الأخرى، يعني الكوميوتيشن بين الام والجي يساوي زيرو، وهذا يعني أنه لا يوجد اتصال بينهم، وهذا يعني أنه لا يؤثران تهديدا لا يمثلان تهديدا الفضاء ثنائي الأبعاد. أما في حالة الماسلس لا، الأمر مختلف، الأمر مختلف. يعني هنا في الماس لا يوجد بوست، في الماسلس يوجد بوست، البوست أيضا يؤثر، وبالتالي إذا حاولت أن تجعل هذا البارتيكل انفاريانس أو مثلا ثابت مستقر، فإنك محتاج أن تعدل إلى كذا معادلة، منها الروتيشن ومنها البوست. فهذا شيء غريب جدا، بالرغم أن الماس لا يوجد ماس لكن يوجد انرجي. يعني انظر هنا في حالة الستاندر مومنتوم نجد هنا لا يوجد ماس لكن يوجد انرجي يمثل بالكي ثم 0 ثم كي، والكي الأولى للماس والتي تتعلق بالزمن، الزيرو الثاني بالنسبة للإكس كومبوننت، والزيرو الثالث واي كومبوننت، والكي الرابع للزد كومبوننت. لكن انظر إلى ما يتعلق بالزمن هو كي ليس زيرو. طيب بما أنه هكذا يتصرف، إذن من أجل أن نجعله انفاريانس تحت الروتيشن فإننا لابد أن نفعل أيضا البوست، وربما البوست متعلق بالكي الموجودة في الماء في التايم كومبوننت، حتى نجعل التايم كومبوننت لا يتأثر، فإننا محتاجين أن نفعل آليتين، آلية الروتيشن وآلية البوست معه. وكأنما نقول أنه إذا تغير الروتيشن يجب أن يتغير البوست، وإذا تغير البوست يجب أن يتغير الروتيشن. وهذا يعطينا فكرة على أن الفوتون يسبب تهديدا للفضاء ثنائي الأبعاد غير المتناظر، لكن من أي ناحية؟ أنا أعتقد أنه من ناحية الشحنة، لأن الفوتون يتفاعل بالشحنات، والفوتون لاحظ أن الفوتون يتفاعل بالطاقات القليلة اللي هي طاقات المدارات الخارجية للذرات، هي تعتبر طاقة قليلة بالنسبة لطاقة النواة، وأيضا يتفاعل بطاقة النواة. يعني نحن نرى أن من النواة تخرج الجاما ريس، من المدارات تخرج جميع الطيف كهرومغناطيسي، ابتداء من الاكس ريس بالمدارات القريبة من النواة إلى الفيجوال الفيجوال ريس اللي هو الأشعة المرئية، حتى تحت الحمراء تخرج أيضا. بالتالي الفوتون يتفاعل بكل هذا، هذه صفة غريبة جدا للفوتون، يتفاعل في كل هذا، يتفاعل بالطاقات القليلة، يتفاعل بالطاقات الكبيرة. فهذا أمر غريب جدا للفوتون، ربما ناتج من هذه الخاصية أن شحنة الفوتون تسبب تهديدا للفضاء ثنائي الأبعاد. طبعا الشحنة تهديدها للفضاء ثنائي الأبعاد أقل من الكتلة بكثير جدا. يعني إذا عوضت في معادلة الطاقة، تعال نذهب لمعادلة الطاقة، هذه معادلة الطاقة. إذا عوضت بدلا من M عوضت Q اللي هي الشحنة، وبدلا من G عوضت الK وهي ثابت كولوم، وستجد أن الشحنة أو القوة الكهرومغناطيسية تأثيرها في الفضاء ثنائي الأبعاد أقل بكثير من الكتلة. يعني من أجل أن تجعل E أقل من الزيرو، أقل من الواحد أقصد، فإن الكتلة تصل إلى هذه المرحلة قبل الشحنة. يمكن أن تعوضها مباشرة، بس يجب أن نتأكد أن الشحنة لا يمكن أن تزيد من الواحد. يعني حسب كتاب الحرارة 35 الذي وجدت أن الشحنة بالنسبة للملاحظ القريب للبروتون وجدتها تساوي 10 أس ناقص 12، وبالنسبة للإلكترون 10 أس ناقص 15. يعني حتى للملاحظ القريب الذي طبعا الملاحظ القريب يرى كتلة ضخمة جدا. يعني البروتون بالنسبة للملاحظ القريب لا يراه 10 أس ناقص 28 كيلو جرام، وإنما يراه 10 أس 10 كيلو جرام. الإلكترون ليس 10 أس ناقص 31، وإنما 10 أس 8 أو أس 7 كيلو جرام. هذا الملاحظ القريب. أما الشحنة بالنسبة للملاحظ القريب للبروتون في النهاية يراه 10 أس ناقص 15، وبالنسبة للإلكترون 10 أس ناقص للبروتون 10 أس ناقص 12، والإلكترون 10 أس ناقص 15. إذا الشحنة مهما كنت قريب منها ستجدها أيضا ضعيفة. وكون أن الفوتون يتفاعل عن طريق شحنته، هذا يعني أن شحنته مكدسة لدرجة كبيرة جدا، بحيث أنها تسبب تهديدا لفضاء ثنائي الأبعاد وليست الكتلة. وهذا ما يجعل الفوتون يتفاعل في جميع الطاقات كهرومغناطيسيا، وأيضا يتكور على نفسه ويصبح مادة وليست موجة، يصبح جسيم بفعل هذه الشحنة. وأيضا نجد أن لا يتفاعل كتليا إلا في مستويات ضيقة عندما تزيد الشحنة عالية، أو عندما تكون التفاعل قوي جدا كما يحدث في الأنوية اللي هو في النشاط الإشعاعي. وطبعا النشاط الإشعاعي في مسافات ضيقة هي 10 أس ناقص 18. فنجد هنا أن الفوتون يتفاعل. لهذا نجد أنا أقول أن الفوتون يسبب تهديدا للفضاء ثنائي الأبعاد من خلال الشحنة، ولهذا نجد متغيراته كثيرة. طيب تعالوا نواصل.
Space of states spanned by all these states with a specific momentum k, s. So we have fixed k, variable s. So there are a discrete number of states here with different spin degree of freedom, but always the same k. So this is a subspace of our one particle system. On this space, this operator W mu, which we defined yesterday, this acts within the space. So in other words, it doesn't change the momentum. If you act with W mu on any such state, you will get another one of this same set of states. And this W mu is a 4-vector operator, so it has 4 components. Each component is one operator. And what are those operators? The components of W mu are always the little group generators. Namely, in the case of massive particles, the W mu operator has the upper index, W mu with upper index is the following 4-vector of operators, namely 0 and then J vector times the mass. Okay? J vector is the vector of the angular momentum operator in x, y and z direction. So in this, what we have identified here, the angular momentum operators are the little group generators for our specific momentum. And for massive particles, this W mu contains exactly here the angular momentum vector. and here it contains 0. So the statement is correct. The components of W are the little group generators. The proof is your exercise. And for massless particle, m square equals 0, W mu has the following form, namely this k value times jz, b, a, and jz. Okay, so it has the spin or angular momentum in z direction in the 0th and in the 3rd component, and it has these new operators b and a in the middle. So again, the 4 components contain 3 different operators, and these 3 different operators are exactly the generators of the little group of this particular momentum. So you see that this operator W mu, which we have defined yesterday, has an interesting meaning, namely it contains these little group generators, and the little group generators in turn have the meaning that they define how the internal spin degree of freedom acts, how it behaves. Switch on the light. Acts. How it behaves. Switch on the light. Okay, now we need to go on with our table. Let's continue with our table, and we now need to determine this structure of the little group in more detail. In physical terms, we are now investigating the nature of the spin, the behavior of the spin. So let's compare here massive and massless. So for the massive case, as I said, we can learn a lot from the non-relativistic limit, and in fact you already should understand what the meaning of the spin is, and because it just is the behavior of ordinary angular momentum in the rest frame. So we have a rest frame, the particle is at rest, it doesn't move, and it can be rotated in all directions. That's it. That's what you know from a particle at rest. And so the spin is therefore the angular momentum at rest. As simple as that. That's what you are familiar with. Spin is the angular momentum at rest. And it's we had also the question, what should be defined as the label of the spin, this S. So we have some additional operator which we can diagonalize. So which operator could we now, for example, diagonalize? We could, for example, diagonalize Jz, the operator spin in z direction, on this space of the particle at rest. These 3 angular momenta, they don't commute, so we cannot simultaneously have eigenvalues of all angular momenta in all directions, but we can select one, for example, angular momentum in z direction at rest, which is the spin in z direction, and we can use that as the additional label. But let us write down the commutational relations first of all. What are the commutational relations of our generators? You know them, they are the beloved angular momentum commutation relations, but let me write them down in a certain way, namely Jz, commutator with Jx, or with Jy, and let's write it down all in one go, namely plus minus I times Jy. What is the meaning of this combination Jx plus minus I times Jy? Who knows it? Better operator, so they increase or decrease the Jz quantum number and the eigenvalue, right? So it's also J plus minus. So, and the result of this commutation relation is simply plus minus this same thing jx plus or minus I times jy. That's what we mean by ladder operators. So this bracket is reproduced here with plus minus. So that's what we mean by ladder operators. Okay, so jz with these x and y give jx and y, as you know. What happens if you do the commutator between jx and jy? So between those two, what you get, you know it of course, you get jz, I times jz. Good. Okay, so far so good. Ladder operators and the thing that you increase or decrease can be constructed by the commutator of the other two. Okay. What are the commutation relations of those three operators? So jz, comma, and let me just do it in the same way. A plus minus I times b. Why not? So it's an exercise. Let's not do the calculation here, but I invite you to do it at home. It's of course a simple calculation by just plugging in all the indices in the general relationship, and then you see that jz A contains rotation around the y-axis, so A contains jy. The result will be jx, but B contains jx. And on the other hand, A also contains a boost in x direction. If you rotate a boost in x direction along the z direction, you get a boost in y direction. B contains a boost in y direction. So you can sort of sense, if you do a commutator of jz with A, you get B. If you do a commutator of jz with B, you get A. You can sort of guess it, and you can check it exactly. And you get it with certain plus minus 1 prefactors. And if you do this combination, what you get is exactly the same as on the left, namely you get plus or minus A plus minus I times B. Okay? So you would see that A and B behave exactly in the same way as jx and jy on the left. They behave like ladder operators which could increase or decrease the jz quantum number. So far it looks very similar, but now comes a very crucial difference. Namely, what happens if you do the commutator of A and B? If you do the commutator of A and B, you cannot reconstruct jz. You cannot reconstruct jz, but you get 0. A and B commute. You can check it directly by explicit calculation. That means even though they can raise or lower the jz quantum numbers, you cannot obtain jz on its own from a commutation rule. And that has a decisive consequence. Namely, suppose jz has a non-zero eigenvalue. Then here it is actually possible that at the same time A and B have 0 eigenvalues. 0 eigenvalue of A and B is compatible with non-zero eigenvalue of jz. And that is never compatible here. Here if jz has a non-zero eigenvalue, but jx and y have 0 eigenvalues, then you get a contradiction. Non-zero here and 0 there, that doesn't work. So if you have a non-zero eigenvalue of jz, you automatically also have non-zero action of the other angular momenta. And that means that if you have a particle which is polarized in z direction and you do a rotation along any other axis, you get of course a polarization in the other axis. It's just a rotation. So you can rotate your particle. You have some axis polarization, maybe in z direction, and you can rotate the particle into any other polarization. Here, however, it is possible that the particle is polarized in z direction, but the action of all the other operators is actually 0. So let's write it down. That is possible while A and B are 0. And then you have diagonalized actually all three operators simultaneously. These two have zero eigenvalue, and that might have a non-zero eigenvalue. So this is mathematically possible. And it's not mathematically possible here. And so the physical observation now is that actually all massless particles which have ever been observed behave exactly in this way. They behave in a way that the eigenvalues of this A and B are only zero. So never has a particle been observed with a non-zero eigenvalue of this A or B operator. All the observations are compatible with zero A and B, but non-zero JZ eigenvalues are observed. And so we have to accept this as a physical observation. All massless particles, all massless particle states, have A equal B equal 0, but possibly JZ non-zero. Okay, and then we can now conclude and write down our result for what is the meaning of spin and what is the label S of our particle states. So the irreducible representations of this little group here is just the angular momentum group, and that means all the possible particle types are labeled by a quantum number J corresponding to the total angular momentum at the rest frame, which is integer or half integer. So J must be an element of this set. It corresponds to the total spin, and the meaning of this is the J square in the rest frame. It's the angular momentum square in the rest frame, and this has the eigenvalue J times J plus 1 as usual. And then we can label the states K, S such that S corresponds to the eigenvalue of JZ, for example. So the spin in Z direction. And that means that spin has the same meaning as in non-relativistic quantum mechanics. Okay, but what about the massless case? Here in the massless case, the irreducible representations, or in other words, the possible types of massless particles, they are characterized by a quantity which is the eigenvalue of Jz. This can still have some value, and that eigenvalue is called the helicity. It's the helicity of the particle S, which is the eigenvalue of Jz for states K, S. Okay, and the momentum of those states is along the z-axis. That means this helicity is the spin or angular momentum in the direction of momentum. That is the meaning of helicity. And so now we see that actually if we do Lorentz transformation, our general Lorentz transformation, then this eigenvalue cannot change anymore. So this helicity is actually Lorentz invariant. And so it can take only a single value. Whatever eigenvalue we happen to have, it's the same for all states of this particle type. there is one exception. The exception is if we have a parity transformation and nature allows such a parity transformation or a reflection. Under a reflection, angular momenta are transformed to minus themselves. So if nature allows such a parity symmetry operation, then also minus s is a possible eigenvalue. And for example, for the photon, that is possible. The photon is such a massless particle, and it allows reflections. And then the photon can have plus or minus a certain helicity, and in the case of the photon, that helicity is actually 1. So the photon can have helicity plus or minus 1. But whenever you fix one helicity, then under these Lorentz transformations, the helicity does not change. So the possible states of such massless particles are either only k, s with a fixed s, or k, s and k, minus s with a certain s. With a certain s. Let me just add one sentence of a kind of conclusion in order to connect it again to the behavior of this operator W mu. Because as we mentioned before, this W mu operator contains in its components the generators of the little group. So this is the operator you want to consider if you want to investigate all of this in detail. And so it's now interesting to record what is the behavior of W mu in the two cases as well. So massive case, m square equals 0. Then I already wrote down what W mu is. And then the square, W square, W mu is given by minus mass square times J plus 1. So the eigenvalue of this W square operator, which is Lorentz invariant because it's a Casimir operator, is the combination rest mass square times the total spin of the particle. And this W square, if you act with it on any state of this particle type, it will always give you this eigenvalue. So it characterizes the spin. And in the massless case, this W square would actually be 0, as you can see from here. It would be 0, so W square has 0 eigenvalues, but if we also know that A and B are now 0, then it's good to look at the components, even W mu. W mu has then these components, JZ. In the rest frame it was JZ, but in general I can actually write down W mu on any particle state of this type, P comma S, has the following form, namely it is given by S times P0 times, times P mu acting on the same state. So let me remove, so this doesn't look very good. The operator W mu acting on a particle state of this type is related to the momentum operator P mu by the simple proportionality. And the proportionality constant between the two is the helicity S of the particle. That is the behavior of this W mu in the case of massless particles. And this relation is valid for all states of this type. And from our calculation here on this blackboard, it follows that this relation is valid in the frame of this particular momentum, because there we have the explicit representation for the particular momentum. We know W mu contains the Jz, and Jz gives S. But then afterwards, this and that behave in a Lorentz covariant way, therefore the relationship must be valid in all frames and therefore for all states of this particular particle type. So this ends our discussion of one-particle states. We have learned what the spin degree of freedom actually means, and therefore we have a classification of all possible types of particles that can possibly appear in a Poincare invariant quantum theory. That is quite a deep result, and a far-reaching result too, as I already announced yesterday, because you can interface it to the other result that we have obtained on the possible types of fields in a theory. Okay. But let's first enjoy this particular result. Now we can quantify a little bit this conflict that is already visible, that I already alluded to yesterday. Namely, this conflict is on the mismatch between the possible types of particles and the possible types of fields. And because we will spend a great deal of time in the next weeks to quantize particles of different spin, so we will come back to this a lot. Let me just indicate one example. Let me just indicate one single example. Namely, let us think of spin 1. If you remember yesterday, there we discussed the possible types of fields, and we classified the types of fields according to the representations of the Lorentz group, and there was one field representation which corresponds to the so-called 1/2, 1/2 representation. This would be a spin 1 field, or potentially a field which can describe spin 1, because at least it looks like spin 1, and it corresponds to a vector field, A mu of x. This field has 4 degrees of freedom because it has 4 components. Mu can run from 0 to 3, so it's a 4-component field. Now let's suppose we want to use that to describe spin 1 particles, because we have already seen field quanta will be particle-like. But what do we know about spin 1 particles? We have just learned we need to distinguish between massless and massive. What do we know about massive spin 1 particles? The massive spin 1 particles have a spin degree of freedom, and the spin degree of freedom behaves exactly like you are used to from angular momentum discussion in non-relativistic quantum mechanics. So if a particle has spin 1, it means it is labeled by a spin in z direction, spin z, and spin z can take the values plus, minus 1 and 0. These are 3 different numbers. So you get 3 degrees of freedom, but not 4. So you see a mismatch. You have 1 degree of freedom less for your particles than you have for your field description. But what happens for mass 0? For mass 0, the helicity S is not spin anymore, but the helicity, and the helicity is Lorentz invariant. At most, you can flip it to plus minus S, so if you have spin 1, you might at most have helicity plus minus 1. These are two different numbers. So you see that the mismatch here is even greater if you want to
طبعا هنا لا هذه جزئية محورية، لأنه يترتب عليها أشياء كثيرة جدا. نرى هنا أن في تمثيل البارتيكلز سبين 1 بارتيكل نجد أن الإيمي نيو لها 4 أبعاد 4 degrees of freedom، أو نقول 4 أبعاد. في حالة الفيلد نجد أن سبين 1 ماسيف بارتيكل اللي هو WZ من ناحية الفيلد لها 3 اللي هو سالب موجب 1 وزيرو. سالب موجب 1 تعتبر الدبليو، والزي هو الزيرو. ونجد أن الفوتون لها 2 فقط، وبالتالي هناك حصل كبح للأبعاد في هذا الأمر. هذا بسبب ماذا؟ بسبب افتراضنا أننا يعني عندما مثلنا لورنز ترانسفورميشن، وقلنا يا أخي لأنه في الليتل جروب قلنا أنه نحن يعني نحاول أن نوصل الحد الثاني اللي هو أن لورنز يعني الترانسفورميشن لا تغير الكي وإنما تغير الجي. بداية الحلقة، في بداية الحلقة قلنا ذلك. فنحن افترضنا فروضات، هذه الفرضيات التي افترضناها أدت إلى هذا. نحن أردنا ذلك، نحن أردنا أن يكون البارتيكل أو الفيلد انفاريانس، نحن أردنا ذلك، يعني كأنما نحن قمعنا الطبيعة. هذا لا يعني نتائجنا خاطئة، إنما النتائج صحيحة، لكن هذه بقية الديجريز اوف فريدم هذه أو بقية الأبعاد أين ذهبت؟ هي صح نحن افتراضنا كانت صحيحة، لكن بالنسبة للفري بارتيكلز، لكن داخل التفاعل هذه الديجريز اوف فريدم كانت موجودة. فنجد أن هنا المس ماتش هذا جاء من البارتيكل إلى الفيلد بسبب فرضياتنا، وبسبب أننا يعني أردنا أن نسهل علينا الأمور، وفعلا سهلناها تمام، ونتائجنا جاءت مطابقة للتجارب. لكن في النهاية التجارب ناقصة، لأنه تعتبر الجسيمات التي تخرج من التفاعل في فري بارتيكلز أو في فري اوسيليشنز، لكن داخل التفاعل هناك ديجريز اوف فريدم نحن قمعناها. فما سيقول هنا البروفيسور هنا أنه سيعمل على ما يسمى بالجيج فيكسينج في هذه الحلقة. سيعمل على الجيج فيكسينج من أجل أن يحاول أن يعمل البارتيكل مثل الفيلد. يعني عندما نحل المعادلات كما سنرى بعدين، عندما نحل المعادلات فهو سيكون مضطرا إلى أنه بعد أن يعمل عملية الكوانتيزيشن يعمل ما يسمى بالجيج فيكسين، وهذا ما نفعله دائما الجيج فيكسين. وهناك نوعين من الجيج فيكسين، كولوم جيج والآخر جيج لا أستحضره لكن سنمر عليه. سنضطر إلى ما يسمى بالجيج فيكسين، ويعتبر كونسترينس طبعا، أو يظهر في الكونسترينس مرة أخرى. كونسترينس لعب هذا الدور مرة أخرى. فبعد ما نجرى عملية الكوانتيزيشن سنجري الجيج فيكسين ونعمل مجموعة من الكونسترينتس حتى نحاول نقمع الديجريز اوف فريدم هذه بدل من 4 أبعاد تصبح 3 أبعاد بالنسبة للدبليو والزي، وتصبح بعدين بالنسبة للفوتون. لهذا في الفوتون ندخل البولاريزيشن، والدبليو زي أيضا ندخل البولاريزيشنز. فنجد أن البولاريزيشن في الفوتون هو بولاريزيشن نوعين فقط من البولاريزيشن، وفي الدبليو زي نجد أنه أيضا 3 أنواع من البولاريزيشن على ما أعتقد، سنمر عليه إن شاء الله. فهذا هو السبب. فما علينا هو أننا نحاول أن نجعل الأمر كما هو، ونجعل الطبيعة تسير في مسراها، ونحاول أن نشتغل هذه المعادلات الرياضية ونجد حلولا لها بحيث أننا لا نقمع شيئا من أجل شيء. تعالوا نواصل.
Describe a spin 1 massless particle with a vector field. You have 2 degrees of freedom too much in your field description. And here you have 1 degree of freedom too much. And that is the mismatch that I have alluded to, and the mismatch gets greater and greater the higher you go in spin, because simply there is no one-to-one mapping at all between the field types labeled by J1, J2 and the particle types labeled by spin or by helicity. There is really very different behavior of the 2 types of objects that we have in our theory. And that mismatch means that in our description of particles by fields for spin 1 there will be a great deal of difficulty. And in particular here we need to get rid of 2 degrees of freedom. And how can we get rid of degrees of freedom? We get rid of degrees of freedom by gauge invariance. And by constraints that we discussed in the first lectures of our semester. And so therefore you see here from this conflict of integer numbers that something deep has to go on. And there is not even only gauge invariance in the sense of unphysical degrees of freedom that can be gauged away, but there is more to it, namely the interactions that spin 1 particles can possibly have must be gauge invariant interactions, and that means spin 1 particles must, for example, couple to conserved currents like the electromagnetic current, which is a conserved quantity, and the theory becomes inconsistent if you would couple such a gauge invariant, such a spin 1 particle, massless particle, to a charge which is not conserved. That is a non-obvious statement, but it's a very important statement. It's a prediction of the quantum field theory framework for all possible interactions of massless spin 1 particles, and this prediction of couplings to conserved currents is observed in nature as well. So it's a very deep and very profound general prediction which is in agreement with observation, and this follows here. You see it already happening from this conflict between fields and particles. Okay, but this is only an indication, and of course we will do it now step by step, and our approach of the next few weeks will be to quantize fields and to obtain the resulting particles in our description as the outcome of our field theory quantization. And we will not start with this case, but this will be our final case, and before we will practice with spin 0 and then spin 1/2, and finally we will come to the spin 1 case, which will have these interesting features which we will then also discuss in detail. Okay, but this is just to let you know that something interesting will happen, and that is also why I wanted to show you this background information. Here the Poincaré study, and before also the study of gauge invariance and constraints in the Lagrangian framework, such that you can afterwards understand how it is all connected. Now we have more time, and we can begin with our first real section of the quantum field theory lecture this year, which is not background information but actual information, quantum field theory information. This is our section 2, and it is the section on the quantization of such fields, and we will begin with the quantization of free fields without interactions, and that we already give us a lot of insight on what I said before and also much more.
تمام، خلاص نحن نقف هنا إن شاء الله، ونبدأ إن شاء الله الفيديو التالي من خلال من هذه اللقطة. وعرفنا أنه يعني من هذا الفيديو نحن خرجنا أنه ربما أن يكون الفوتون لديه نوع من الكتلة، ليست كتلة كما هي المعتادة، إنما شحنة عبارة عن شحنة كهرومغناطيسية عالية تعمل على تهديد الفضاء إلى أبعاد غير متناظر بطريقة أو بأخرى، وهذا يجعل الفوتون يتفاعل في الطاقات العالية والطاقات المنخفضة. طيب، السلام عليكم.